Okay, so I said we were going to take a look at some practice problems, and I'm just going to solve them on a blank document here. So it's question 12.24 is the one that I had in the slides. And in the first one, we're taking an alkyne. So we have this terminal alkyne here, and then we're converting it into a primary alcohol. So we're going from there. There we go. So we want to take this alkyne and convert it into a primary alcohol. So you can see there's no change in the carbon skeleton here. We're starting out with 7 carbons and we end up with 7 carbons. All right. Now we know that in order to make a primary alcohol, we have a couple of ways that we could do that. But one of the best ways would be well, actually, there's a few ways you could do this reaction, isn't there? Anyhow, does anybody have any ideas? Anybody want to tell me what their strategy was, where they started? I think there's probably 3 different ways I can think of doing this.
What I did was
Yep.
for the first reagent, I put H2 and then Lindlar's catalyst, and then I put the BH3, the THF, and the H2 with the NaOH to add in the primary OH.
Absolutely. So what you're saying is that you did this to reduce it to the alkene, and then in the next step, used hydroboration oxidation. So let me just scribble in here. Okay, and that is going to give you, well, I guess I don't even have to draw it. So there you go. That's going to give you the product just like that. Okay, so yeah, I give that 100%. That's perfect. There's nothing wrong with that at all. I say that's perfect. Let me just go over a couple other strategies with you then, okay, just to kind of flesh out some more ideas. So I'll just copy this and let's see if we can come up with another way. So I'm going to do this one in, we'll change the color. We'll do this one in blue, okay? So I would say another way that you could do this would be to use 9-BBN. So if you use 9-BBN, so that would give you an enol, right? It gives you an anti-Markovnikov addition of water across the triple bond, which tautomerizes to give you an aldehyde. So in the first step, you use 9-BBN, and then in the second step, you use H2O2 and sodium hydroxide, and that is going to give you the aldehyde. Okay, so that's going to give you this aldehyde. So we have 1, 2 carbons like this, and then to reduce that to the alcohol, you could either use lithium aluminum hydride, so LAH, or you could use sodium borohydride. I'll just use sodium borohydride because it's one step, and you can do that in methanol, ethanol, or water. So there you go. There's 2 ways of doing it, and I'd say there's even a third way to do it. So let me paste it down here. Come on, you. There we go. So if we try it in red, let's try and switch our colors up here. All right, so, I didn't give myself a lot of space here, but if we start with what Sanika said, so she said, okay, reduce using H2 in Lindlar's catalyst, okay, that gives you the alkene. So we could make the alkene. Then we could do an anti-Markovnikov addition of HBr using HBr and peroxides. That would give us the primary alkyl halide, and then we could just treat that with sodium hydroxide, and that's just going to do an SN2 to displace the bromide, which is a great leaving group. So really, I see 3 different ways of doing it. I wouldn't say that any one is better than the others. I'd say the first 2 are 3 steps, the last one's 4 steps, but that's comparable enough that there's no big difference between any of them. So yeah, I would accept all of these. The thing I like about this one is you get to use a reaction that we just learned in this chapter. So there you go, 3 different ways to do that one. All right, let's try the next one. So this is 12.24, and this is B. So we're going from propanol or propyl alcohol, and we want to make propyne. Okay, so we want to make this compound. So we're not changing the carbon skeleton. Again, we're starting with 3 carbons, and we want to end up with 3 carbons like that. So in terms of making an alkyne, we really only want to know one way of doing that. So if I just do a little bit of retrosynthesis, we know this compound has to come from this vicinal dibromide. Then we treat it with excess sodium amide. followed by treatment with water. So then the question becomes, well, how do I get from here to here? Well, if I do another retrosynthetic step, I know the only way I can make that dibromide is from propene, right? I have to make it from this compound and treat it with Br2. So then the question comes, well, how do I get from here to here? I'd say there's two possibilities. I could either just cook it up with acid, and that's going to give me the alkene. There's no Zaitsever-Hoffman in this case. It doesn't matter. Or you could treat it with tolusyl chloride and pyridine, and then a hindered base, which won't do a nucleophilic attack. It'll only do an elimination. So either one. So what is that going to look like? So I'm going to write it all out here. So I like the sulfuric acid way of doing it. So did I just lose everything? Great. Okay, so let me rewrite it here. So 12.24B. So we'll start out with our primary alcohol. And we want to make the alkyne. So again, I'll review my retrosynthesis. So I said we have to make this from the dihalide. And then we have to make this from the alkene, like this. So in our first step, we're going to treat this with sulfuric acid and heat. So we'll just put concentrated sulfuric acid and heat, and that would give me the alkene. Now, alternatively, you could say 1 tolusyl chloride and pyridine, followed by a non-nucleophilic base like DBU or DBN, right? That's not going to give you any SN2. So that would give you this compound. And then the next step is going to be to treat it with bromine. So we'll just put Br2, and that's going to give you the vicinal dihalide. And then the last part, you're going to treat this with excess sodium amide, followed by treatment with water. And that's going to do the double elimination followed by proton transfer. And that gives you the final product, lo and behold. All right. Give me a thumbs up if you're with me on that one. Any questions about that guy? Right, there's should be a lot more reactions bouncing around in our head now, okay, than there were in organic chemistry 1, right? Let's try C. So this is 12.24 C from the Klein textbook. So we're starting it with 1-butene, this compound, and we want to convert it into an aldehyde. So hey, we're going to have to use some oxidation here. Now, is there any change in the carbon skeleton? Starting out with 4 carbons, I'm ending up with 4 carbons. Did anybody have a strategy for this one? Anybody have a strategy for this one? Where they started or? Yeah, go ahead, Sanika.
Oh, sorry.
Does anybody have an idea? I don't see many ways of doing it, okay? So, okay, I see what you're saying. So you want to make some kind of alcohol and then oxidize it with PCC. I like the idea of using PCC in the second step. Yes, so we'll put here PCC. The problem with just using H3O plus is if we just use H3O plus, right, that's going to give us a Markovnikov addition. So that would give us this alcohol. We don't want that alcohol, right? We want the primary alcohol. So we're going to have to treat it with chlorine and THF, right, followed by hydrogen peroxide and sodium hydroxide. And that is going to give us the primary alcohol, this guy. There you go. Then you could treat that with PCC, right? And that's going to work. So PCC and dichloromethane. For this step, you could also have used the Swern would work. You could use the Des-Martin periodinane. That would work. And you could also use, well, you can't use chromic acid. So you could have used the Swern or the Des-Martin periodinane. Either one is fine. Okay, now we're on to 12.24D. So we'll put here 12.24 D, like this, and we're taking the secondary alcohol. This is 2-butanol, and we want to make butane. All right. Anybody have a strategy for this one? Like, I want to make an alkane. That's not so exciting, is it?
For this one, I did the concentrated H2SO4 with heat, and then the H2P2 just to convert it to that.
There you go. That's the best way I can think of. I can't think of a better way than that. So treat it with concentrated sulfuric acid, heat it up. Why do we do that? Because it causes the loss of water. You make the alkene, and then you just use hydrogen and platinum, and you're done. Yep, I'd say that's the best conditions I can come up with for that one. I mean, you could do longer. You could do tazol chloride elimination and then reduction, but I mean that's an extra step, so it's not necessary. So I like the way you did it. That's how I would have done it too. All right, let's try the next one. So it was 12.26. Let me just find a new page here. So this is 12.26. And this first question, I like it because we are changing a carbon skeleton. So we're starting out with this aldehyde, and then we're making a ketone. So let's do something like this. So we're making this ketone. So if we count the total number of carbons in the starting material, we have 8 carbons in here. Then we have 6, 7, 8, 9, 10 carbons in here. So, all right. So if you notice, what you have to do is you have to add these 2 carbons. Could anybody tell me what the strategy would be to add those 2 carbons? And there's really only one way we could do it based off of what we've covered in our class. Anybody tell me how you would add those 2 carbons? Cha, absolutely, I love it. So, yep, my students are saying is step 1. So it's going to be a Grignard reaction, right? So I'll just put here, number 1 is going to be ethyl magnesium bromide, followed by treatment with water. Or you could put, yep, aqueous acid. Yes, let me just draw the intermediate. So you would end up with this alcohol. And then if you want to convert the alcohol into the ketone, you could really use anything. So Anastasia, you put what? PCC? Yep, that would work. So PCC and dichloromethane, okay? Or you could have even used the Jones oxidation. So, or you could use sodium dichromate, sulfuric acid, and water. Or you could have used the SWERN. We could practice writing those out. So step 1 is DMSO and COCl2, oxalyl chloride. And the second step is triethylamine. So we could do that. Or you could use the Des-Martin periodinane. Any one of those would work in this case. Yeah, great. Awesome. Let's try another one that's in the same vein. So let's see here. Let's try. So this is 12.26B. All right. So if we take this compound, so we have something that looks like this. So this aldehyde, and we want to convert it into this ketone like that. I'm sure you guys figured this one out faster than I did. Anybody have a strategy for this one? Yeah, same strategy as an A, but with ethyl magnesium bromide, methyl magnesium bromide. Absolutely. So first step is going to be methyl magnesium bromide, and the second step is going to be H3O plus, and that's going to give us the alcohol with our extra carbon, and then we just oxidize it. Let's use chromium trioxide, aqueous acid, and acetone just to mix it up. And there you have it. Great. Awesome. So does it matter if we have to put magnesium bromide or magnesium chloride? No, it doesn't matter. So for a Grignard, usually, like let's say you wanted to make a methyl Grignard, it's usually going to be methyl magnesium bromide or methyl magnesium chloride. It's usually those. Magnesium iodide, I guess sometimes you could make it, but it's usually one of these, either one of those, and it doesn't matter which one you would pick. Either one would be fine. The reason why it's usually these ones is because alkyl halides like methyl bromide and methyl chloride are abundant and cheap. Iodides are more expensive, so usually we buy the methyl magnesium bromide or methyl magnesium chloride. All right. There we go. So that covers all of the content in chapter 12. I just wanted to go over a couple more problems with you. So I was looking through the practice problems in the book. Now, they're all good. And of course, we don't have time to go through every single one. You want to try them on your own time. But I did see some other ones that I thought were pretty good. Okay. So I wanted to go over with you, if we have time. It's 12.39D. Okay, 12.39D. And I know I didn't give you a break to try this problem. I just want to take a look at it as a group. So you're starting with acetylene, and then you want to make this ketone. So 1, 2, 3, 4, 5, 6, 7 carbons. Okay, so you want to make this ketone from acetylene. There's really two ways you could do this. Okay, but I kind of want to walk you through it because it looks like a really difficult problem, I think, when you first look at it. Okay, but you guys are aware of that you can, since we have terminal terminal hydrogens on here. Okay, we have one here and one here. You know that you can deprotonate using sodium amide, and then alkylate using an alkyl halide. So we're going from a total of 2 carbons to 1, 2, 3, 4, 5, 6, 7, 8 carbons. I guess I lost my oxygen there. So there's 2 possibilities here, but I'll show you one that I think is good. And if we think in terms of adding carbons, okay, so if I was to think about my alkyne as coming from this part of the molecule right here, okay, if I think about my alkyne as coming from this part of the molecule, then what I could do first is I could add these 3 carbons, okay, and if you're wondering why would you do that, let me show you why, okay. So I'm going to add 3 carbons on the end. So the first step is going to be sodium amide. And the second step is going to be propyl iodide, right? 1, 2, 3 carbons. So I'll put 1, 2, 3 carbons and then iodide. So that would give me 1 pentyne. It would give me this compound. Now, I could add the last 2 carbons in a Grignard reaction if I converted this to the aldehyde, right? So what I'm saying is, in terms of my retrosynthesis, 1, 2, 3, 4, 5, if I could have this aldehyde, which I know I can make directly from here, then all I have to do is add the last 2 carbons through a Grignard. So if you're a little unsure of what I'm talking about, let me show you. So the next step would be to do 9-BBN, an anti-Markovnikov addition of water, okay, which is going to tautomerize to give you an aldehyde. So we have 1, 2, 3, 4, 5. Here's our aldehyde. So now you can see the end game, right? We take this and we treat it with ethyl magnesium bromide, followed by water or aqueous acid. Either one is fine. So I feel like this problem is one that looks really difficult when you first glance at it. But once you see it done, um, usually I think students would be able to pick up on this one pretty quickly. The key is figuring out that you've got to make this compound. And to me, it's remembering that when you take a terminal alkyne and you treat it with 9-BBN, you get an aldehyde, right? Of course, you do an anti-Markovnikov addition of water and you make a 1, 2, 3, 4, 5. So you end up making this enol, but the enol is not stable, right? It tautomerizes to give you the aldehyde. So I thought that is a good problem. All right. Any questions about that one? Just give me a thumbs up if you see where the answer comes from, if it makes some sense to you. Okay, great. Awesome. Okay, there's 2 more I wanted to take a look at with you. And the next one is 12.39E. So 12.39E, it's not long. So 12.39E is this problem here. So we're starting with a secondary alcohol. Okay, and then we want to convert it to another secondary alcohol, but we have a change in the carbon skeleton. So if you count the carbons here, we have 1, 2, 3, 4, 5. So we have 5 carbons here, and then we have 1, 2, 3, 4, 5, 6. So we need to add another carbon here. So usually I think students can figure out, well, it looks like I need to add this carbon here. So what's the strategy? The strategy to me would be if you had this aldehyde, right? Then you could just treat it with methyl magnesium bromide to add that last CH3 group, the one in the red circle. So then the question becomes, well, how do I get from here to here? Because if I oxidize this compound, it's going to give me this ketone, right? That's not what I need. I need to make this, alcohol so I can oxidize it to the aldehydes. So now we need to move the alcohol around. And you can't just use sulfuric acid in this case, because if you were to heat this, if you were to use H2SO4, so concentrated H2SO4 and heat, that's going to give you the Zaitsev product. That gets you nowhere near where you need to be. What you need to do instead is you need to put the double bond here. So that means we have to do tosyl chloride and pyridine to make the tosylate, and then use a bulky base like potassium t-butoxide, and that will give us the terminal alkene like this. So now we can do an anti-Markovnikov addition of water. So use BH3 THF followed by H2O2 NaOH, and that's going to give us the primary alcohol. Then I'm kind of running out of space here, so I'll keep going down this way. So then we're going to oxidize this using something like PCC, which will give us the aldehyde. And then to get to our final product, we're going to use methyl magnesium bromide or chloride, followed by treatment with H3O plus, which is going to give us the alcohol that we want. So we're going to have the hydroxyl group here, and now we have our extra carbon like that. Again, I think it's a really good problem. I think it's a good way of presenting some of the reactions that we've learned. Boros, a little bit of organic 1, organic 2. All right, so there's one more I wanted to take a look at, and then we'll call it a day on chapter 12, and we'll move on to chapter 13. The last one I wanted to look at with you was question 12.39 and F. So 12.39F, where we take this terminal alkyne, and I want you to try to convert it into this ketone. All right, I want you to try to come up with the reaction conditions to convert it into that ketone.